So 2012 Level 3 Physics on Waves, Question 3, the laser pointer. Mira is playing with a laser pointer. She finds that the laser spot on the wall has changed when she puts dress fabric in front of the laser. With no fabric, the spot looks like that, round and relatively clear. With fabric in front of the laser pointer, the spot looks like this. Explain why the threads in the fabric have caused the light to spread out in a pattern as shown in the photograph. So here's my laser pointer here. It's shifted like sideways, causing a sort of a cross effect from the original. So we're explaining why that has occurred in that pattern. You could get into a heap of detail, and it's a little bit subtle or vague, if you prefer, how much detail they're after, but the marking schedule labels this as a merit level question. And from that, I wouldn't get into too much detail. You have to talk about it as interference. There's clearly interference, and there's interference in a vertical way from the gaps in the thread, and in a horizontal way from the gaps in the thread, and that's causing this this vertical and horizontal interference pattern. So in the vertical way, you've got gaps between the threads, and that's causing diffraction in a vertical way. And then in the horizontal, you've got gaps between the threads horizontally, and then they're just over the top of each other to produce the whole plus kind of a diffraction pattern. So if you imagine you get a diffraction pattern with your bright fringes, something like that, in that sense, but we'll make them wider because they're, and it'll look exactly the same. Then you've got your vertical ones as well. So it'll be strongest in the middle. There'll be a little bit of diffraction further that way because of the left-right diffraction, and then there'll be, as I said, a little bit of diffraction vertically as well because of the up-down diffraction. That means that in the center it's going to be the strongest color, which is what we see in our diagram over here, and it's going to start fading out in those directions with practically nothing in these directions, because that's where you don't have any slits causing diffraction in that manner. So I guess that's what they're after. That was actually pretty long, but yeah. Anyway, B, moving on. I'm predicting that there'll be something getting into a bit more detail later, although the earlier questions in this waves have been pretty tricky, so maybe they won't. Mira tries a different piece of fabric. The laser spot is spread differently because threads in one direction are much closer together. So without getting into the question, you can see that the threads excuse me, must be closer together on the, let's see, we've got n lambda equals d sine theta, or n lambda equals dx over L. So d is our spacing of threads, thread spacing, the distance gap between the successive gaps, and x is our distance on the screen. Okay, so this is more useful to us for understanding this. If you increase d to get the same, for the same wavelength and the same bright fringe being and the same length of distance between the two, the screen and the fabric, your x is going to have to decrease. So vertically it looks like x has decreased, which means your distance of spacing would have increased. Okay, and horizontally, yeah. Anyway, describe how. Okay, I think I might have begun answering the question. Actually, maybe not specifically. Looking carefully, Mira can see vertical stripes across the laser spot. So they're specifically after vertical stripes. Describe how the light passing between the threads causes this pattern. So it's clear that the stripes are due to interference between the waves diffracting from gaps between the different threads. And I think the marking schedule is very minimal in here. If you just said interference, that's not too different from the first question, which it's diffraction causing it. But this first one, maybe it's. I don't like the marking schedule answer for this, so I'm going to try and tease this out a little bit more. Describe how the light passing between the threads causes this pattern. So the light passing between the threads has to diffract, and it'll diffract according to this equation here, because it's a you could use d sine, yeah, because it's a small angle approximation would work, because the distance of spacing from the screen to the fabric will be quite a bit larger than the distance between the fringes. So we can use our small angle approximation of sine theta equaling x over L. But anyway, so the light causes this by diffracting and then interfering. And it'll diffract according to the equation with the small angle approximation. Okay, that covers enough of it, I think. It's more than what the answers give you, but the question is a bit vague. Mira investigates further. She finds out that the laser has a wavelength of 650 nanometers, not surprising since it's red, Wascally Wabbit. Old movie reference, don't worry. Cartoons. When her fabric is 40 centimeters from the screen, the stripes are 1 millimeter apart. Use this information to calculate the separation of the close woven thread. So we're looking for D. Its fabric is L equaling 40 centimeters, 40.0 centimeters, 3SF given to us. The stripes are 1 millimeter apart, so X, let's see, this is a little bit tricky. X equals 1 millimeter. Yeah, I'm just thinking, if they're talking about the stripes being 1 millimeter apart, that means for n equals 1, that's fine, yep. So for n equals 1, you'd have 1 millimeter, so let's just use that. N equals 1, x equals 0.001. If we're considering it in meters, that means L is going to be 0.400 meters. What else? What other information do we need? In lambda we've got is the 650 nanometers, so we're going to use n lambda equals dx over L, because our small angle approximation definitely applies. 1 millimeter is much smaller than 40 centimeters. So if we plug that in, what are we trying to find? We're trying to find D. Rearrange for D, and you'll get D equals 2.6 times 10 to the minus 4 meters. So that's the space, a very small spacing between the gaps in the fabric. Okay, I'm taking my time too much. Moving on. The fabric is stretched a 16 centimeter length of fabric, pulled out to become 16.3 centimeters long, pulling the close woven threads further apart, so the gaps are now, if you consider them a particular distance of spacing, which is what we calculated above, D, it's now going to spread them further apart. Okay, so now we've got a new D, we'll just call it D dash. Calculate the new separation of lines on the screen. So we're looking for X dash. If we were to look at our equation, do this in a different colour, for X equals N lambda L over D, none of this has changed. So L is the same, wavelength is the same, and if we consider N equals 1 the same, then we're trying to find a new spacing X for a new D. You can just plug in all of your old numbers. Can we do that actually? No, we can't, because we don't, this is a trick, we don't know what our spacing, well, I guess you could calculate it if you wanted to. You would say 16 is now 16 over 0.3, and that equals, your D original was 2.6 times 10 to the 4 over your new D, so it's D dash as I had before, and you could just rearrange that and plug that new number in. In fact, that seems the easiest way to do it. Or you could just use that ratio and work out what D dash is multiplied by in this situation. So D dash, if you put it in terms of the original D, so you would have D dash equals D divided by whatever this number is, equals, we'll just call that times times D. Is that right? It would actually be the inverse of that, so it's going to be 16.3 over 16, and then that's going to be the new factor that you multiply, that makes sense, because you've stretched it, so it's got to be greater than 1 for the spacing stretch as well. So you plug in that number, you're dividing by a higher number, so x is going to decrease. You can just take the x value from above, which is 1 millimeter, or 0.001 meters, and divide it by that 16.3 over 16. And whatever you get, in this case it's going to be 0.98 times 10 to the minus 3, so 0.98 times 10 to the minus 3 meters. So it's 0.98 of a millimeter is what the new separation lines on the screen will be. Okay, I've made that longer than it probably should, so we'll call that quits.